Alrighty, morning everybody. Welcome back to Calc 1, where students are dropping like flies. Let's hope you are not next. So the plan for today is we're going to finish off our discussion of Standard 17 and then jump into Standard 18, where we're going to be talking about how do you find areas of various shapes. I've got my usual office hours today at 11 and 1, tomorrow at 10 and at 1. And as far as the homework goes, we're going to have a quiz over the optimization stuff on Friday in class. I'm not posting a web work for the optimization packet, mainly because the web work questions for optimization are all terrible. So what I do instead is I'm going to post my quiz solutions, or not quiz solutions.
Dang it.
Hate smack him. What I'm going to do is I'm going to post my worksheet solutions for Standard 17. There's several optimization problems from this standard that we won't talk about in class. I encourage you to try those out on your own and use my solutions as sort of a practice guide for getting ready for this quiz on Friday. So with that, any questions or comments before we get started for today? When given a choice between eternal bliss and a ham sandwich, which will a mathematician choose? True mathematician will always choose the ham sandwich. Because after all, nothing is better than eternal bliss. But a ham sandwich, that's better than nothing.
Yep.
Okay, so when we left off last time, we kind of talked about the optimization process. I think we were in the middle of looking at this fishy example where we have, we sort of had this rectangular plot that was getting fenced in. Here's a fish. I'll let the fish be happy today. That's supposed to be a smile. Where we're fencing in a rectangular area with a width of W and a height of H. And what we had said last time was we were told that the maximum amount of fencing that we could use was 100 feet of fencing, which told us that the perimeter of our fenced-in area, which you all said was 2H plus W, should come out to 100, assuming we use all of the fencing that's available to us. And our goal is to maximize the area of the fenced-in area, which is height times width. So we can't maximize area by taking the derivative right away, because currently our area formula has two separate variables in it. So what can we do to get our area formula just in terms of a single variable rather than two of them? Jonah?
Using the other equation, you find a way to get either W or H by itself.
Yeah, exactly. We could take our perimeter equation, which gives us a way to write W or H in terms of the other variable. So Jonah, you propose we solve we write W in terms of H or H in terms of W?
W in terms of H.
Okay, get W by itself?
Yeah.
Cool. So if 2H plus W is 100, what's W going to be equal to then?
Negative 2H plus 100.
Yeah, it's going to be negative 2H plus 100. So that's the part of the process that I described as part 3 on the front page, which is take the expression you want to actually maximize or minimize and write it in terms of a single variable. Which in this case, if area is height times width, you can replace our W with negative 2H plus 100 to get H times negative 2H plus 100, or negative 2H squared plus 100H. So now the function we're actually trying to maximize, the area here, we have written in terms of just a single variable. So here's a question. What do we we do with our area formula now? Area is just written in terms of h. How do we find the value of h that's going to maximize that? And you see me glaring. James?
So now we need to look for the maximum of that function, and to do that we need to first find the critical points.
Yeah, we need to find the critical points of this function. So how do we find our critical points? I've been doing this for the last couple standards now, so. John Henry?
Take the derivative.
Take the derivative. All right, it's going to give us negative 4h plus 100. And Katie, what should we do with that derivative?
Then just do 4h equals 100. Solve for h.
Solve what for h? Right now we just have an expression. We need an equation if we want to solve
So
for h.
set it equal to 0.
Ah, set it equal to 0. I like it. Yeah. Critical points are where the derivative is 0 or undefined. There's no values of h that are going to make negative 4h plus 100 undefined, so we just need to set that equal to 0 to solve for h, which will give us 4h is equal to 100, or h is going to be 25. And if h is 25, that's going to give us w is negative 2 times 25 plus 100, which is negative 50 plus 100. I think we're going to get that w has to be equal to 50. Or 25 and 50 watts. So what's the units on our h and w here? Morgan?
Feet.
Yeah, it's going to be feet. Since we were told we have 100 feet of fence to work with, perimeter is being measured in terms of feet. So amount we use for our height and width are also going to be feet. If I ask you, by the way, for what the, I think I just asked what's the dimensions of the maximum area. If I ask you for dimensions, you just need like the h and the w. But if I ask you for, say, what's the maximum area that could be enclosed, you would then have to plug those numbers in to solve for the area. So we get 25 times 50, which is 125, 1,250 square feet, I think. So, how do we check to make sure we found a maximum for the area? We only had a single critical point, but there's no reason theoretically why that critical point could have been a min or a point that's neither a max or min. So how do we show that h equals 25 is going to be maximizing our area?
The second derivative test?
Second derivative test. Okay, a double prime of h is negative 4. Say what?
That didn't work.
Technically, we didn't talk about how you could use the second derivative test to find absolute maxes and mins. But you could say something like, oh, the second derivative is always negative. That means the only critical point has to be of absolute maximum. That the second derivative is always going to be negative. If we use the way we talked about on the front page, though, what we would do is we would use the first, or the second page, I would say. We would use the first derivative test. Say, we take 8 prime of h when h is 25, we get 0. And if we wanted to take, say, 8 prime of, Emma, what's something to the left of, what's a point to the left of 25 we can check?
20.
All right, if you take a prime of 20, I was going to say a prime of 1, but a prime of 20 will do, I guess. We'll get negative 4 times 20 plus 100, which appears to be greater than 0. Negative 80 plus 100 is positive 20. And if we take a prime of a point to the right of 25, Lauren, what's a point to the right of 25 we could check?
26.
26. Man, I was going to say a million. We could check a prime of 26 to get negative 4 times 26 plus 100. No, man, this I'm not confident enough. I'm going to have to actually compute this out. Thanks, Lauren. We'll get negative 104 plus 100, which is going to be less than 0. So what does that tell us? Well, I would say it's going to tell us that since a prime of h is positive for all h less than 25, and a prime of h is negative for all values h greater than 25, what does that tell us about a of h? If your a prime, your derivative, is positive everywhere to the left of your critical point at 25 and negative everywhere to the right of 25, what does the first derivative test tells us is happening at h equals 25? Charlie?
Give an absolute maximum.
Yeah, we're going to have an absolute maximum. Absolute, because the first derivative is positive always to the left of 25, and the first derivative is negative always to the right of 25. You can say a of h has an absolute maximum at h equals 25. So what's the moral of the story? Moral of the story is, when you're doing this sort of optimization process, let's give this fish some glasses. When you're doing the optimization process, you always want to start by finding formulas for the things you'd like to evaluate. In this case, the perimeter is 2h plus w. The area was height times width. We were given in the problem that the perimeter is equal to 100 feet of fencing. We find a way to write the function we actually want to maximize or minimize in terms of a single variable by using this constraint here. We were able to solve this for w and then plug that expression back in to the original area formula to get area just in terms of h. And then once you get to that point, then it basically becomes a standard 15 problem where we find our critical points and then show we found the max or min using the first derivative test. Yeah,
What's the last thing you wrote? A of h has an absolute maximum.
A of h has an absolute maximum at h equals 25 feet. Yeah, sorry, that's supposed to say at. Questions, comments, concerns? So, we know burrito. So that tells us how we do kind of go through and work out the optimization process. So I encourage you to take a look at some of the other problems in this packet. They're all going to have a similar sort of nature where it might help to start by drawing a picture, write out your formulas. Dr. Gerstle, do we have to know things like what's the volume of a cylinder or area of something scary? No. Here's what I want you to know. Let's say I give you like a rectangular prism shape, like a box. which is going to have a width of W, a length of L, a height of H. How would you find the volume of that box? Morning? Yeah, it's going to be length times width times height. You multiply them all together to get your volume. Find the surface area. This one's a little trickier. Well, I would say you add the top area at the top plus the bottom plus the front plus the back plus the sides. Nest top.
So it would be like 6 times WH.
If this was a cube,
Oh,
I don't think this is necessarily going to come out to be a cube, say. What would the area at the bottom of this box be? James?
WL.
Yeah, it's going to be W times L, width times length for the area of the bottom. The bottom's just a rectangle. Take width times length of that rectangle, leave the area. And the top's going to be the same, so this is going to come out to 2WL. How about the area of the front and back, kind of the side that's jumping out of the board at you in this beautiful 3D image, and the side that's going back deep into the board? Hey,
WH.
yeah, WH. Yeah, I had to second guess myself there. Yeah, so we're gonna have 2WH if we take the front and back sides and add them in. And finally, how about the sides, the right-hand side and the left-hand side? Megan?
2 times LH.
Yeah, LH for each side, so since we have 2 of them, it's going to come out to 2LH. I'm going to give you a hint. It might behoove you to remember how do you take the surface area or the volume of, say, a box like this, or say, a potential quiz question. So what I encourage you to do is to work through some of the the practice problems in the rest of the packet. Like I said, I'll have my solutions up on Canvas in the usual spot, and from there, we're going to move on to Standard 18. Start talking about how do we find areas of things that are not so nice. 2, 3, 4, 5. Or 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7.
We're gonna need one more.
We also need one more.
Someone's hoarding packets. Oh, well, look who it is. At least in this one. All right. Finally at the last kind of what I would call major unit of the semester that we're going to be looking at. Now that we've kind of talked about how to use the derivative to solve a variety of word problems, the last kind of major theme in Calc 1, and this is going to lead us into the biggest theorem of the semester, the fundamental theorem of calculus, and a couple standards from now. How do we find the area of a shape? So, for instance, we're talking plenty now about how do you find the area of a rectangle. You just take width times height. What if we have a triangle? Let's say we know the height and the width of that triangle. If it's a right triangle like this, how do we find the area of said triangle? Who remembers their high school geometry rules? John?
Width times height divided by 2.
Width times height divided by 2. Sound good, James? Okay. I'm going to write it as 1/2 width times height. Same thing. How about the area of a circle of radius r? James?
Pi r squared.
That's a bad sentence. Pi is squared, please. Yeah, we have area of pi r squared. All formulas that you're used to working with, that you have lots and lots of fun experience with, I'm sure, from math classes back in your heyday. How do I find the area of this thing? A little bit less simple. So, this is a question mathematicians have been interested in for thousands and thousands of years. How do you find the area of weird shapes? And this is kind of known as the area problem. Like, we know how to find areas of lots of kind of relatively simple geometric shapes. Things like rectangles and squares and triangles and circles, etc., etc. But it was an open question for a very long time. How do we find the areas of not so nice shapes? Because finding the area of something like that, I would say, not so simple. So what we're going to be doing for the next few standards, actually for the rest of the semester at this point, is we're going to be talking about, first of all, how do we approximate areas of shapes like this, and then the last couple standards, spoiler alert, this is probably the third to last standard. So this standard, we're going to be talking about how do you approximate the area of a shape like this. Last couple standards, we're going to be talking about how do you find exact formulas for the areas of wacky shapes like this. So I have a question. What does this shape look like at the kind of the top side of this wonky? I don't know what to call this shape. Does anybody have a good name for this shape? All right, I'm going to call it a quargle. Does anybody? What does the top side of the quargle there look like? Okay.
A parabola.
Looks like a parabola, you say. That's interesting. Kate says that the quargle looks like or at least the top of the quargle sort of looks like a parabola. Franklin?
Triangle.
A triangle? Sort of, yeah. Triangle, I think, would be a little bit more straight edges and a little bit less curve to it, but it definitely looks sort of triangular, I would say. Kate, I'm going to go with your suggestion. That sort of looks like a parabola to me. In fact, a parabola is what I was going for when I drew that. So if we were to graph a parabola, say, I don't know, y equals x squared, I don't know, let's pick out two values of x, like say x equals 5, x equals 1. And if we kind of look at what lies underneath the parabola from x equals 1 to x equals 5, if you ask me, that sort of looks like the quargle. At least that was my attempt at trying to draw the quargle on the board. So we can sort of say the quargle looks like the area underneath the function f of x equals x squared from x equals 1 to x equals 5. So, Dr. Gerstle, okay, why are we doing this? Who cares? Well, the whole idea of what we're going to be doing in this standard is we're going to be asking the question of how can you approximate the area of a weird shape like the quargle? No, I hadn't come up with a name for this before today's class. I'm glad I chose quargle. It's a fun name. To try and say what's the area of the quargle, we're going to ask the question of how can we try and approximate the area underneath this parabola from 1 to 5. So, okay, how do we approximate an area like this? That's kind of a weird question to ask, Dr. Gerstle. What we're going to do is we're going to use simple shapes to help us approximate the area of the crazy shape. So, Nathan, out of these three formulas for areas, rectangle, triangle, circle, which one do you think is kind of the easiest or the simplest to work with? Rectangle? You just multiply two numbers together, width times height, right? You don't have to divide by 2, you don't have to square anything, you don't have to multiply by a horrifyingly scary number like pi that brings back nasty trigonometry memories. Areas is going to be, of a rectangle is going to be pretty simple. So here's what we're going to be doing in this standard. We're going to take a function like f of x equals x squared. We're going to try and draw a bunch of rectangles that look like they're very close to matching up with the curve. Like so. And what we're going to say is, if we can find the area of these rectangles and sort of add them together, what we should ultimately get is an approximation for what's the area underneath the graph of our function f of x, which in turn is going to tell us what's the area approximately of the quargle. And that is going to be the game plan. So some of what I just said. The goal is to approximate areas. And the way we're going to do it is we're going to represent the area underneath the function f of represent as the area underneath some function f of x from x equals a to x equals b. So like for instance, we took our quargle here, represented it as saying, that looks like the area under the function y equals x squared from 1 to 5. We're going to use rectangles to approximate this area. And then, since Nathan likes working with rectangles so much, he says that the area of a rectangle is pretty easy to find. You just take width times height. Our last step is going to be to add the areas of each of our rectangles together. And that will give us an approximation for what's the area of the original shape, like say the core. So any questions or comments before we move into looking at some specific examples here? Question. Is anyone here a big Star Wars fan? Sort of? Of course, the two students who are speaking up are going to speak up. All right, James and Joe. Let's see if you know this piece of Star Wars knowledge. What is the best Star Wars character?
Obi-Wan Kenobi.
Obi-Wan Kenobi?
Chewbacca.
Chewbacca? These are both good ones. These are both incorrect answers. That is less of a good answer. Unless you subscribe to the Darth Jar Jar theory, which makes him a lot cooler. Anybody know what the correct answer is? Yoda's up there. No. Best Star Wars character, bar none, R2-D2.
I was gonna guess that.
Adorable little guy. Always gets the job done. You need something hacked, he'll hack it for you. He's going to take on a battle droid, he'll spill it with oil, light it on fire, and then fly away as it burns to death. No, that's episode 3. No, R2-D2 is by far the best Star Wars character. If you disagree, you're wrong. He's amazing. Plus when he gets damaged, he makes adorable little screaming noise, like wow. And it's like, oh my gosh! Even when he's like not kicking ass, he's still being awesome and adorable. Dr. Ursula, where are you going with this? Why are we talking about R2-D2? Why not talk about R2-D2? We should do that more. Also, I want to talk about R2, which is going to be a specific area approximation for what does the area look like under this function. I know, here comes the fun. So what does R2 stand for? R is going to stand for right. Specifically a right endpoint approximation. And what does the 2 stand for? 2 stands for the fact that we're going to use 2 rectangles to get there. So what does that mean? Well, if we sketch out a graph here of y equals x squared from, say, 1 to 5. So this is kind of the... So, in other words, here's our quargle again. We're trying to approximate the area of the quargle. The 2 rectangles approximation means we're going to draw out 2 separate rectangles that hopefully match up with the area underneath this curve from 1 to 5. 1, 2. These are going to be the 2 rectangles that we have to work with. So here's a question. Why do you think I called this a right endpoint approximation in drawing this picture? What about these 2 rectangles, in other words, would you say somehow coincides with the idea of being on the, using right endpoints? Okay?
So we use when we're drawing our rectangles, we use our right corner of top right corner of the rectangle is on the graph, and we draw it left over, so we start at the right, work our way to left.
Yeah, exactly. The way I drew, if you notice, the way I drew these rectangles is I wanted the top right corner of the rectangles to actually be points on our function f of x. So our top left corners of the rectangle are just kind of floating in space above our function here. Our top right corners, though, both happen to lie on on the actual function itself. And we'll contrast that here in a minute when we do a left endpoint approximation where the left endpoints, the rectangles will match up. And then the two rectangles, well, two rectangles. So I'm going to call this this rectangle's area, area 1, and I'm going to call this rectangle's area, area 2. So here's a question. What's the width of each of these rectangles? We're going to need to know their width and heights if we want to find the areas of each rectangle using our rectangle area formula. How do we determine what the width of each of these rectangles is going to be, assuming the two rectangles have the same width? Morgan?
2.
How'd you get 2?
5 minus 1 divided by 2.
Yeah, so the width of the rectangles is just going to be the length of the interval divided by the number of rectangles that we want to use to kind of fill it up, which in this case, we have an interval of length 4. 5 minus 1 is 4. And we're dividing by 2 rectangles, which is going to give us 4 over 2, which is going to be 2 for the width of each of our rectangles. We're going to have one rectangle, in other words, going from x equals 1 to x equals 3. Another rectangle going from x equals 3 to x equals 5. So we know width of that one's 2, width of that one's 2. How do we find the height of each of these rectangles? So let's start with maybe A2. If you notice, the top right corner of this the top right corner of our rectangle matches up with the value of the function f of x. Where here we're looking at the function f of x equals x squared. So how do we find what's the y-coordinate of that point? In other words, how do we find the height of that rectangle? Yes, James.
You plug 5 in for f of x to get 25.
Yeah, because if you notice, if we sketch this out, at the point x equals 5, the height here corresponds, or the y-coordinate of this point corresponds to what we would get if we plugged 5 into the function f of x. So the height of this rectangle, in other words, is going to be a height of f of 5, which will be 25 once we plug it into the function, because f of x is x squared. Reagan, how about our height of the first rectangle? We do something similar to tell us how tall this rectangle is.
You can plug in 3 into the function.
Yeah, because if you notice, what we get on this function is f of 3 on the right-hand side, because the top right corner of the rectangle matches up with the function f of x. So if we take the height of that point there, we're going to get a height of f of 3. So we'll get a height of h equals f of 3. So if we want to find our good old approximation for our dear friend R2, well, we would take the area of the first rectangle plus the area of the second rectangle. How do we find the area of the first rectangle? We know what the width is. We know it has a width of 2. Same with the second rectangle. So we can plug in 2 for the width and f of 3 for the height of our first rectangle. And for our second rectangle, we'll have a width of 2 and a height of 5.
determine the heights of 5 and 3?
The heights of 5 and 3? Good question. Are you wondering where 3 and 5 come from, or how we get those numbers?
Where do they come from?
Well, I would say if we look at our two rectangles, one goes from x equals 1 to x equals 3, one goes from x equals 3 to x equals 5. If we take our first rectangle, if you notice, the height of this rectangle right here, or this top right corner, I should say, that's a point on the graph of f of x. Specifically, this point right here is the point 3 comma f of 3. What we would get if we plugged x equals 3 into the function for an x coordinate, and our y value would be, well, it would be 9. Because if you plug in 3 into the function f of x equals x squared, you would get 9 as an output. So the height is basically just going to be the y coordinate of this point, because the distance from f of 3 to 0 is just f of 3. And similarly, with our second rectangle, since the top right corner matches up with our function f of x at x equals 5 here, this point right here should have an x and y coordinate of 5 comma f of 5, which is going to tell us that the height of that rectangle should be equal to f of 5.
Yeah, I get that, but why did you choose 3 and not 3.5 or 4?
Well, because in order to get two rectangles that go from 1 to 5, if we want the rectangles to have the same width, they have to have a width of 2. So one goes from 1 to 3, the other goes from 3 to 5. And the fact that we're using the right endpoint of each of these rectangles means we use sort of that right coordinate. We'll do the same thing with the left endpoint approximation here in just a minute. So, any other questions about where these numbers are coming from so far? Rhoda, what's f of 3?
9.
Yeah, that's just going to be 3 squared, which is 9. How about f of 5?
25.
That's going to give us 5 squared, which is 25. And that just came from plugging in f of 3 and f of 5 into our function f of x equals x squared. If we had a different function, you would just plug those into the formula of whatever function you're working with here. And then, well, now we just need to add it up. We'll get 18 plus 50. It's going to give us a grand area of 68. So what does that tell us? Well, that's going to tell us that the area under the graph of f of x equals x squared from 1 to 5, and thus the area of our quartal, is approximately 68. If we added our two rectangles, that gives us 68 as their area. So, question. Is 68 too big or too small? In other words, did we find an overestimate for the area or an underestimate? Looking at our picture here. John Henry?
Overestimate,
Why do you say overestimate?
because the rectangles go above the parabola.
Yeah, it's because the rectangles that we're looking at include all of the area that we care about, which is this area right here, the quartal area. But there's also a little bit of extra area going on. This area that I've kind of X'd out. So 68 is probably an overestimate for the actual area. Questions or comments? So we know our area is less than 68. How can we maybe get an underestimate for the area? We kind of have an upper bound on how big the area of the quartal could possibly be. Let's put a lower bound on it. And to do that, we're going to do a very similar process, but using a left endpoint approximation. Using R2-D2's evil brother, L2. So I'm gonna graph this up again. So L2 is going to be a left endpoint approximation with two rectangles. Which means, once again, we're going to draw out two rectangles and try and approximate the area under this curve using those two separate rectangles at the approximate area of the quadrille. So, what do you think is going to make a left endpoint approximation different from the right endpoint approximation? Because we're going to have two rectangles again, but they're going to be not quite the same rectangles as they were before. So how do you think we might draw our rectangles differently? Aiden?
We start from, instead we start from the left side and draw over to the right about with an equal width. So our left point will be on the graph and our right point will be off.
Okay, so in other words, with R2, the top right corners of our rectangles kind of both happen to lie on the function. This time we're going to have the top left corners of our rectangles lie on the function. So instead of having a rectangle, our first rectangle from x equals 1 to x equals 3 match up with f of 3, it's going to match up with f of 1 instead. So this will kind of be our A1 area. And instead of for our rectangle from x equals 3 to x equals 5, instead of having the function match up in the top, or the rectangle match the function in the top right corner, let's do it in the top left corner instead. And that'll give us a nice underestimate, judging by the picture, for what's going to be the area of the quadrille. Or in other words, the area under our graph of f of x equals x squared from 1 to 5. So the idea here is our top left corners are on the function rather than our top right corners, which was the case when we drew our rectangles in the R2 approximation. So I think our widths are still going to be the same. We're still going to have w equals 2, w equals 2 for the widths of both of our rectangles. So they go from 1 to 3, 3 to 5. Franklin, what's going to be the height of our first rectangle here, do you think?
1.
What's that?
1.
How'd you get 1?
Because the point is on the 1.
Yeah, in other words, you take just f of 1. Just like over here, when our endpoints were at f of 5 and f of 3 for the endpoints used to find the height of each rectangle. Here, this is at the point x equals 1 on our graph, so this point right here is 1 f of 1. So the height of our rectangle should just be f of 1, which is 1 squared or 1 at the end. Lou, how about the height of the second rectangle? F of 3. Yeah, because our second rectangle matches up with the graph of f of x at x equals 3, the left endpoint of the rectangle. So the height of this rectangle, you would then expect to be equal to f of 3. So if we do our L2 approximation, what I think we're going to get is area of the first rectangle plus area of the second, which is width times height plus width times height. Well, the width in both cases is 2. The height of the first rectangle is f of 1. The height of the second rectangle is f of good old 3. Which is 2 times 1 squared plus 2 times 3 squared, which is 2 plus 9 times 2 is 18. I'm getting 20. as our L2 approximation. Which tells us then that the area would be roughly equal to 20. Taylor, how do we know that 20 is going to be an underestimate for the area, just looking at our graph?
Rectangles don't fill up the entire parabola.
Yeah, this time our rectangles don't give us enough area. There's all this, I don't know, I'll call it polka dot area, that the rectangles aren't giving us underneath the graph of the original function. The rectangles are contained in the quargle that we care about, but they don't make up all of the quargle. So this 20 here is going to be an underestimate using our picture here. Okay, who wants to be engineer for a day? Morgan. Let's say you're an engineer, Morgan. You're trying to build a quargle-shaped bridge. Bridge doesn't make sense. You're trying to form a quargle-shaped area, and you need to know what the area of that quargle is. You come to me, Dr. Gerstle, mathematician professional. Stop laughing. And you say, Dr. Gerstle, I need to know what the area is. I don't need an exact number for the area, but I need a pretty good approximation so I can use the quargle in some engineering project of mine, because I, Morgan Iverson, am an engineer professional. I tell you, oh, the area is bigger than 20 and less than 68. Are you happy with that approximation? Yeah?
No.
No? Yes? Do it?
Do better.
Do better. Why are you unhappy?
It's too big of a range, doesn't tell me.
It tells you something.
It's not true.
It tells you it's less than 68 degrees. But you're right, that's not a very good approximation. That gives you a whole range of like 40, a size 48 that the actual area could lie in between. How can we do better? So right now, saying, oh, the area is greater than 20 is less than 68, it's like, Dr. Gerstle, go home, you're drunk. Give me something I can actually work with. So how do we get a better approximation? James?
Add more rectangles.
Add more rectangles? So you're saying if we did it with more rectangles, we should get like a tighter range of values?
Yeah.
Interesting. So what James is proposing is that, let's go from 1 to 5, our quargle, that if we have more rectangles that we're using than 2 rectangles, we'll probably get a much better approximation to what the actual area is than we would just using the 2.
Yeah.
Yeah, I would say so. If you look at these 2 rectangles over here, if we did a right endpoint approximation, there's a lot of overhang because the rectangle has the same constant height from 3 to 5, but f of x, it changes height quite a bit as you go from 5 on the right-hand side down to 3 on the left-hand side. That's giving us a lot of extra area. But here, if we use smaller rectangles, the overhang is a lot less, I would say, than if we were to use, say, only 2. If we were to kind of graph out what would the 2 look like on this graph, it would be like if we wanted to try to find the area of these 2 rectangles right here, which has a lot more overhang than if we split it up and just used a bunch of narrower, skinnier rectangles. So in other words, what James's idea is, use more rectangles for a more accurate area approximation. How are we doing on time? Oh, we're still doing great. Doing great. But y'all know we're doing great. I'm glad.
Or another way to take it would be to add the areas of the triangle under. You can find the area of a triangle under that curve right there.
A triangle.
From 1 to 3, connect the two endpoints.
Ah,
Because we have enough information to find that triangle.
I like your first idea better.
Yeah.
You know what point I'm going to try and ultimately make, don't you? We could do that. There's lots of ways we could get better approximations. We could try and take off the R2 approximations, say, hey, we have two triangles right here. Or two shapes that are very close to being triangles. Let's subtract that off and we'll get a much better approximation. Another way we could do this is to say, instead of using the right endpoint of the rectangle or the left endpoint of the rectangle, let's use the midpoint. Give us a little bit of overhang and underhang at the same time. That would probably get us a better approximation. So, professional engineer Morgan.
Yeah.
We have lots of different ideas for how can we find areas under, how we can get better approximations. Which one do you want to go with? Oh wait, I'm the mathematician here. You're an engineer. You don't know anything about math. I don't care what your opinion is. I'm sorry. Is that too harsh?
No. I was actually gonna say you are the mathematician.
Oh, okay. That's right. Let's do the same process again. So I'll write this up here so we don't forget it. Areas between 20 and 68. Let's do the same process, this time using 4 rectangles. I think there is an R4 in like episode 1 of Star Wars.
Isn't it like the weird orange one?
Yeah, it's like the weird orange one that I think just like dies very quickly or something.
Yeah.
I don't know. It ain't no R2, but we'll give him a shot. So R4, you can probably guess, just like R2, except we're going to divide up the area this time into 4 rectangles instead of just 2 of them. So if we're going to divide up the area from 1 to 5 using 4 rectangles and a right endpoints, what's going to be the width of each of those rectangles?
1.
How'd you get 1?
Well, there's 4 of them, and you're starting on the left of the first one and the right of the last one, so 4.
Yeah, well, we have an interval of length 4. We want to divide it up into 4 separate equally sized pieces. Each one's going to have a width of 1 in order to make that happen. Because if we do that, we'll get our width. Once again, if we use the same formula we did on the last page, we'll get W, our width, is going to be the length of the interval divided by number of rectangles, which in this case is going to be 5 minus 1 over 4, which is 4 over 4 or 1. So our rectangles are going to be twice as skinny as the previous ones. With 2 rectangles, they each had a width of 2. With 4, that width gets cut in half to give us a width of 1 instead. But if we're doing R4, we're still going to draw it out so that the right endpoints, top right corners of our rectangles, all match up with the function, which still f of x equals x squared. So, question. How do we find the area? So this time we're going to have 4 rectangles to deal with. All of which are going to have a width of, not 2, a width of 1 this time. Emma, how did you find the height of the first rectangle, the A1 rectangle?
You would, using f of 2.
Top right corner comes from x equals 2. So we'll have f of 2 is the height of that rectangle. The A2 rectangle, Eden? This rectangle, how do we find the height?
You would take f of 3,
It'd be f of 3,
which
which will be 9. Plug that in the next step. A3 rectangle, Carson? That's going to be f of 4. And finally, how about the A4 rectangle, Kate?
F of 5.
F of 5. Right at this point. Which if we add those up, we'll get f of 2 plus f of 3 plus f of 4 plus f of 5. Since our function's x squared, we're just going to take 2 squared plus 3 squared plus 4 squared plus 5 squared. And we'll get an area approximation of 4 plus 9 plus 16 plus 25. 13 plus 16 is 29, plus 25 is, I believe, 54. On the other hand, we go through the same process. This time we'll go with L4, where we take the evil clone of R2D2's weird brother. It's almost like a double negative makes a positive. What would we get? We'll do this quickly, that'll let you go. Well, using the left endpoints, you would get something like this. We'll have an A1, an A2, an A3, an A4. Pretend these all have the same width, please. They're all going to still have a width of 1 if we're doing an L4 approximation. Except this time, Liam, what's going to be the height of the first rectangle? Yeah, it's going to be 1, coming from the fact that you would take f of 1. So that's going to be 1 times f of 1. Second one would be f of 2. Third one would be f of 3. And the fourth one would be f of 4, which would be 1 squared is 1, plus 2 squared is 4, plus 3 squared is 9, plus 4 squared is 16. And we come out to 25 plus 5, I believe, is 30. Okay, professional engineer Morgan.
Yeah.
You said that going from like 20 to 68 was too big a range. I've now narrowed it down to saying it's between 30 and 54. Is that good enough for you?
It's better. Yeah. If it's good enough for you.
Well, I'm asking you, is it good enough for you? You're the engineer, you're the one who needs this data.
Yeah, it's good.
Morgan's happy with it. If you all ever need to hire an engineer, don't hire Morgan. She uses very vague approximations for things still, apparently. So, when we come back on Friday, we'll do standard 17 quiz and then kind of look through the rest of this standard by looking at more examples of putting this idea into practice of rectangle approximations of areas. Have a good one.
Thank you.